to switch from security back to insecure AI. I had some discussions with some of you about security and AI. I think one thing about AI, yeah, it's kind of tricky in terms of security. I'm going to try to move a little bit faster than yesterday, just because, we have a lot of stuff to go over. Yesterday I wanted to take it slower so that, you guys can come up to speed, but maybe we can move a little bit faster. And if there are any questions, I'm going to basically try to answer those and things like that. So, and now I'm going to ask Professor Ambika to please don't give a bad example to the students. Yeah. Okay, so again, this is an NVIDIA accelerator. It's kind of the next to last generation. This makes everything possible in terms of training. I should also mention that probably you have noticed that I sent another assignment for this afternoon. So there's going to be some more hands-on, and this one is going to be about training. So you are going to actually train a network on Colab, and hopefully that's going to go well. An important chip, and I should mention that now I'm going to have several slides, maybe a little bit less than 10, with different examples of hardware accelerators for AI. Until now, we talked about AI, how the algorithms work. Now, a few examples on how, the hardware people try to solve those. Again, it's about the same models, but they are going to look very differently on different accelerators. I have slides, detailed slides on each of these accelerators. We are not going to have time this, 5 days to go over all of them. So at some point so take notes, and you will need to, will vote, will be democratic, which ones to go in more details, not today, but, so GPU, NVIDIA is one. TPU, so this is tensor processing unit from Google. They've had 4 or 5 generations already of this. This is an interesting one. That's the largest, hardware chip that you can have, because they literally, and I have a photo of myself with one of these, maybe I should share it. But they basically take a full 300 millimeter, 12-inch wafer. Is basically as big as a, as a dinner table. And they make the largest square chip out of that. So, this is on the diagonal here, it's 30 centimeters. And, it's 46,000 millimeter square, 2.6 trillion transistors. Yeah, so this is for Cerebras. And right now, like I said, is the largest. Another interesting one for fans of FPGAs and field programmable gate arrays. This is an example of an accelerator which kind of mixes features of both regular, ASIC kind of chip and an FPGA, and it's called, and I'm not sure how many people have heard the term coarse-grained reconfigurable array. Okay, a few, so that's good. Yeah, so CGRA, this is actually a very popular, a way of designing accelerators, because you do, these models, algorithms, they keep evolving, right? And if you build a chip that's hard-coded, ASIC, when things change, it's kind of stuck. So you need to design the next chip. An FPGA allows you to build any hardware, but it's not very efficient because it's very fine-grained. So you design everything with really small things, and it becomes much larger than an ASIC. With a CGRA, you have some larger blocks which are specifically design and optimize in hardware, but you have some reconfigurability. You can rearrange them, and so Sambanova has, and there are a few others. Of course, Xilinx, then the FPGA people, have gone into this AI, and they, in some sense, they do also a combination of a CGRA, of a coarse grain reconfigurable array. Basically, this is kind of a CGRA. And then they also have, obviously, because they are an FPGA, so they have some FPGA fabric that you can design, custom hardware in that FPGA. And basically, this is called Versal. And again, they are pushing very much in the direction of AI. And you can get access to these in some of the cloud. And I think maybe this is the last one. So this is related to how we ended the previous yesterday's lecture, these spiking neural networks. An ideal spiking neural network I had some discussion with some students about emulation and simulation and actual hardware. If you want to have the energy efficiency of a spiking neural network, ideal, you want to implement it, like I said, like the biological brain with actual spikes. But again, we humans have not figured out how to do that properly yet. But if you want to kind of make progress in that direction, you can use you can simulate, so you can have simulators on computers with those spikes, but those are not very efficient, or you can have emulators. So Intel has put together an actual hardware which looks a little bit, in some sense, like an FPGA. It's just an array of and this is all digital. So this is all implemented with digital logic, but the functionality is that of a spiking neural network. So they have events that represent the spikes, and those are in time domain. And they have a network on chip where they send packets around with the spikes. And this is available both in hardware, in the cloud, on Intel facilities, and you can access them remotely, or you can use simulation. They have a simulator called Lava where you can work with this. And there is another company that's doing also somewhat similar. So Loihi is more for the cloud, but there is this company called BrainChip, which is doing also spiking neural networks for the edge. And also kind of the same way. In other words, digital circuits with events in time, but not really truly spiking. Yeah, sure.
Say you are transmitting the spikes in the time domain. So
yeah.
What is the pulse width of the spike? Because the NOC has a finite bandwidth, right?
No. So exactly. So no, it's not the actual pulse. You transmit a packet in which you say at this time, that's what I'm saying, is really an emulation, is not transmitting the actual analog pulse. You are transmitting a packet, a digital packet, like a network packet with headers and whatever, in which you say there is a pulse at this time that happened at this neuron, and then you transmit it, to all the neurons. That, yeah, so it's really just an emulation, is not the actual, yeah. Other questions, by the way? So this is not AI, but in some sense, it's a very important, component that enables much of the AI progress, which is basically 3D memory, 3D DRAM. And again, I had some discussions with some of you about processing in memory, processing near memory. This 3D DRAM allows relatively, so again, you still have the memory wall, but because it's 3D, it's very, close together, and you can also have these very close together to the accelerators. Having this, massive amount of fast memory close by is allowing the the progress in AI. And you can see there are some, staggering numbers here. Basically, 1,000 gigabytes per second bandwidth and 8.4 gigabits per second I/O speed. So, and here you see how they are arranged basically next to the accelerator. So it's important to understand the importance of memory. Something else that, it's kind of interesting to, how many people have heard of Gartner's hype cycle? Okay, just the one professor. Okay, so yeah, then this is, yeah, well, yeah. No, this is an important thing because, again, in terms of, kind of knowing how things work. So there is this company called Gartner that every year comes up with hype cycles for different things that are important. So, and they have one for AI. And the idea is that most things that happen, in society, in, industry, they have this kind of shape in cycle where basically at the beginning there is some innovation trigger, so something happens that basically leads to a lot of activity. And then that raises expectations very quickly. And very quickly, there is, this kind of over expectation, So this is called the peak of inflated expectations. But then reality hits, people, companies need to make money, need to sell product, need to, and then basically there is this basically throw of disillusionment. So, there is some, and finally, when things become more mature, you get basically this slope of enlightenment when people say, okay, this maybe was a little bit overhyped, but there is something there, and then, finally you can get to productivity. And this is just about, AI, and you see there are some things here that are basically, at the peak here or very close to the peak. AGI, artificial general intelligence, edge AI, foundation models, responsible, all these prompt engineering. So all of these are here at the peak, but you see that some of them are already kind of falling. Neuromorphic computing is kind of falling. Generative AI is kind of falling. So we'll see, when they get in this bottom here, somehow cloud AI services for whatever reason are here. But then, you start having the slope of alignment, the autonomous vehicles maybe are, there was a lot of hype, but now maybe there is some reality, and, computer vision is already established. So that's kind of the idea here. And, if you look at, probably here is also interesting for people that are interested in research, quantum AI is just starting. These autonomic systems where you have the, multi-agent systems, all these things. Yeah. Yeah, this is 2023. I showed it here. Yes, sorry, I should have explained that. Yeah, I had it there to see that things are changing quite fast, actually. In just 1 year, I mean, there are some things that are kind of in the same place, but for example, generative AI was here, all the way at the top last year. And by the way, this is 2024, so this year means really last year, but yeah, generative AI here has, yeah. So yeah, this is the previous year.
With the previous slide where you said we are using FPGAs for these AI workloads and
yeah.
you said they are inefficient, but they are very flexible. So I believe Microsoft has a brainwave project. They are using some FPGAs just before their core compute. So is there any particular reason why they need to put FPGA before their core GPU compute server? Like, is there any reason why they are still using FPGAs if they are inefficient?
Yeah. Well, so what does efficient mean? GPUs are not efficient either. Yeah, so if you look, every type of accelerator excels at some aspects of of the AI kind of cycle, from defining the model, training, deploying, inference, whatever. So the reason, well, I'm not sure. Microsoft has been using FPGAs in their servers for decades now, for commercial. I mean, not for AI. And I don't know exactly, but they find, so again, FPGAs give you the advantage, if you have them already there in the cloud, when there is a need for a new application, you can accelerate it, a software application. You can accelerate it by deploying, critical parts of the code in FPGA. And because FPGAs are so versatile, so flexible, it's a very fast process. So that's why they are doing it. Once you are here, in the more, probably FPGAs are going to go away and you are going to have more, but when you are here, FPGAs give you this advantage of very quick deployment. So I don't know the specific example that you're talking about, but I guess that's why they already have them in the cloud. So, already having deployed resource, using it makes sense if it gives you, yeah. Okay, other questions? So again, some more taxonomies about AI. So I'm going to move here. The assignment is with training. So I'm going to have a few slides about training. We haven't talked about this. We just mentioned backpropagation. That's the algorithm for doing kind of the training, but then, the different strategies, there are a few major ones. So supervised learning is the one where, the example that I gave with the loss function, with the cats that you recognize. So this is kind of the traditional, I would say, AI, but then there are a few others, like unsupervised learning, and we'll give you examples. Then there is self-supervised learning, and then reinforcement learning. So all of them have their own peculiarities. So an example of unsupervised learning is just clustering. So you are basically looking at and actually, yeah, sorry, there are two. There is a little bit of animation. So if you are looking at a bunch of points here, you as a human, you kind of see that, there is a cluster here, there is another cluster here, and another cluster here. Again, I had some discussions with one of you. This is not a precise definition, right? So, is this point here, a node here in that cluster, on the other cluster? It doesn't really matter. But this is an example of an unsupervised learning where you want your AI algorithm to be able to detect these clusters and, tell you these points are in that cluster, those points are in that. And this is unsupervised, so that's an advantage. Actually, right now, the whole AI, this is a big effort in the whole AI world to go away from supervised learning. Although supervised learning, was very successful, the problem with supervised learning is that you need data that's labeled. Basically, someone needs to, and that's not sustainable, So these unsupervised learning have been, are basically the new method. Self-supervised learning, these generative neural networks are, again, kind of an example. And then reinforcement learning, which, again, was one of the early but big successes, with the game of Go, with AlphaGo. But again, the way these systems work, the reinforcement learning, you just let them basically play, and play doesn't necessarily have to be a game, but in a game, it's really easy to kind of understand how it works. They just play, and initially they make a lot of mistakes. They get, low scores, but every time, something happens, and in many ways, that's how we learn. Humans, when you learn a game, you learn how to play something, you kind of learn in the same way. At the beginning, you are really bad, and the more you play, the better you get. And these AI systems can get incredibly good. Again, about machine learning. So machine learning was there before AI, in some sense. But the big difference was that the traditional, so machine learning still has this property that you don't really program it, you let it, but it had this, humanly designed features. And then basically, and a good example was for the cats. So a human would create some kernels like the ones, but instead of those kernels being learned by the AI model, those were handcrafted, and then the model only learned, did this classifier. So the deep neural networks, the difference is that all these features are also learned. So just to make sure that, that's kind of clear. And we already saw this AlexNet network, and again, I'm going to move a little bit faster. It becomes relatively complicated. And the other thing that, and this is typical of the early, models, many of these things seem quite random. Why is it 14 by 14 by 256 here, and here is, there are two of them, and then a ReLU, and then one of them, and a ReLU. It's been a lot of trial and error. In some sense, that's what's interesting about these large models with transformers, that they are very regular. So this is in some sense irregular, these old kind of networks. And the main reason was that there was not enough compute power maybe to make them more uniform, and so they were trying to get efficiency by doing it this way. There were some questions about, I think when we talked about the recurrent neural network with the feedback, this was another big kind of thing at the time, to have these residual connections that help with the back propagation. And because once these things became very long, very deep, back propagation had trouble, and these residual connections helped, with back propagation. So again, this vanishing gradient that we had in a recurrent neural network appeared in the non-recurrent ones as well. So this was ResNet. It was a big advance at the time. Now, in terms of terminology, so again, the kind of the foundational data, elements of AI are tensors. So tensors are really generalizations of matrices. So basically, a 1D tensor is a vector, 2D tensor is a matrix, and then you have, multidimensional tensors. In Python, with the NumPy library, you declare them like that. And then other terminology, and, we are going to talk a little bit about that, how you do the training. You basically need to have some data for the training, some data for the validation, and those need to be, they need to be kept separate because otherwise you can run into trouble with your training. And then, there are also concepts about, again, this is a little bit beyond the scope of this class, and some example of adversarial test where some networks are very prone to, if you put a little bit of if you mess around a little bit with the image, some networks can get really bad in terms of being able to recognize, for example, a stop sign, which for us as humans is very easy to still see it. There's also this concept of batches, which is basically about efficiency. You don't want to train, just one at a time. You do it in batches. That allows the GPUs to work in parallel. Yes. Sure. Which one? This one?
Yeah,
or?
this one.
Sure. Next one. Okay.
So this is a common trend that I've seen, like as you start from the input, the number of filters first increase. You can see there are 96 filters.
Yeah. Yeah.
It peaked to something like 384.
Yeah.
And again, it started to decrease from 256 or something. So is there any reason why we are first increasing the number of filters, then slowly decreasing it again?
So I mean, I can give you, some idea. So if you look at the filters at the beginning, they are larger in terms of, 28 by 28 versus 14 by 14. And, it's cheaper. If you want to have more filters, it's easier to have, I mean, again, I'll give you an example. I mean, I'll give you an argument for, kind of computational efficiency. You can have, more of these here than here, because here it would be very expensive because they are larger. So that's kind of one argument. The other argument, so let me get, I'll get to something that I think is relevant to this. Let me keep going. Yeah, so this is a little bit how a deep neural network looks like with the layers, the weights, the optimizer. Yeah, let me get, yeah, so we already talked about the loss function. So here is already something related to your question. There is this concept of hyperparameters. So basically, you have a model and you have, these layers and you have the kernels and, but then you have options about the numbers. Basically your question is about the numbers. Why that many? Why that many? So that has to do with this concept of hyperparameter tuning, because, you can think about the number as a variable that you want to optimize. And again, optimization, and that's going to, be related to my kind of first attempt at justifying those numbers. Optimization is all about trade-offs. So optimization is trade-offs. I have some limited amount of resources, time, compute, GPUs, whatever. And I want with that limited amount of resources to get the best result. It's not the best result, that can be, it's the best result with those resources. So then if I have this option of having more filters that are small and fewer filters that are large, and get a better result because of that, probably that's what my optimization is going to get me. So having, more of the large filters would give me a little bit better result, but, at a much more expense. So that's probably how you get those numbers. So this is, and again, we are not going to have time to discuss about these, but, PyTorch is, there are basically two kind of dominant, and actually right now PyTorch is the one dominant. Used to be TensorFlow, so PyTorch was basically pushed by, Facebook at the time. They are all standard now and open source, but basically Facebook started with PyTorch. Google started with TensorFlow. At the beginning, TensorFlow was kind of more dominant. Nowadays, basically PyTorch has taken over. A main reason is the fact that it's more Python. And like we talked about yesterday, Python kind of has advantages. But basically, there are, examples of some PyTorch syntax. So this is an example. And again, the assignment that you have has, statements like that. So basically, that's how the syntax looks to do a training. How many, what are the arrays, the batch size is 100, how many epochs, training labels, things like that. And, this is one of those kernels that we are talking about. Again, this batch thing, you do multiple of them in parallel instead of doing first this 5, then that 4, then this 0, then that 1. You do all of them in parallel because, again, yesterday we talked about this single instruction, multiple data. GPUs are massively parallel. So you get the biggest advantage if they can do all those computations at the same time, with the same instruction. So, this is a batch, this is another batch. Yeah, so you start with random, and basically one epoch is doing all the batches, and then you do the batches again and again until, and again, I already kind of explained the, the batching. So again, if you do one at a time, you basically go through this process, for each batch. But if if you do 2 at a time, it basically takes the same amount of time, but you compute twice as much. This is about the training versus the test. So you need to make sure to not mix these two because the danger is overfitting. So basically, these models are so large that if you provide the whole training set from the beginning and just that, it can learn it, almost, it doesn't generalize, that's the term. So you want your training, so to give an example, with cats, right? So you want to recognize cats, but if the model can learn, 1,000 cats from a training set, but then if you give it 1,001 cat and it doesn't recognize it, that's a bad thing. And that can happen if your model learns each of those separate cats very precisely, but it doesn't generalize. So having this test set is important. So here I'm going to answer some of the questions about the size of the kernels. So, and again, this is more on intuition, but I think it's important to kind of understand. So basically, when you have a bird, it has some features. It has a beak, it has an eye, it has a tail, it has some wings, it has some legs, whatever. So in some sense, that's what these convolutional neural networks are doing. You basically, let's say you have a kernel for beaks, and if you apply it here, it will have a large value because, you know, it's going to fit. And if you add it anywhere else, it's not going to have a large value. So basically, you know, you can, and again, this is an oversimplification, but that's actually what the humans were doing with those human, you know, with the manual features that I showed at the beginning. The humans were trying to kind of identify these features and create kernels for them. Now, the deep neural networks kind of learn this by themselves, and some of them you can recognize the beak. I'll show you that. Some of them you cannot. Yeah, you had a question?
So first to identify a beak, first I have to identify a bird, the kernel for the bird will be a picker, and then
No. It's the other way around. You start with small features and then you put a bird together from the small features. Let me get going. Let me get going. Yeah, give me 5 more minutes and we'll be done. Yeah, so yeah, this is basically, you know, why this is a justification for why having a convolutional neural network rather than fully connected, because basically the same feature can appear anywhere in the image. So I want to be able, and again, by having a kernel for beak, I can detect it wherever it is. If it was a fully connected, you know, it would be much less efficient. So, you know, if you want an upper beak, a left beak, and a middle beak detector, you know, you can use the same kernel. Yeah, so these are the filters. And yeah. So yeah, this is how it works. I'm going in interest of time, but this is really how the convolutional neural network works. And, you know, for different features, you have different. Now, you know, some of the reasons you have many channels, for example, is RGB. So you have a channel for every color. And then, yeah, so, and we had some discussion about this max pooling. So the, you know, just to justify a little bit the max pooling, when you, let's say, I'm going too much back. When you want to detect this beak, okay, if you know, if you move a little bit to the left or to the right, it doesn't really matter as long as the beak is in that region. So by making the max of that convolution result, you get the important information that, yes, you know, there is something going on there that's related to what that kernel wants to do, but you don't really care as much, you know, exactly, you know, which pixel, so to speak, it's related to. Yeah, so again, this would take too long to this, but yeah, this is basically the max pooling example. So, you know, you have basically this tree here that's really important, this tree here that's really important, and, you know, maybe, so you really only care about some of these numbers, you know, that provides you enough information. And another way to think about it, if you have a high resolution image and you make it low resolution, that's another way to kind of think about max pooling or average pooling. You still have the same image, the same information. So that's another reason, you know, basically. you do this subsampling, and that's the argument. And again, it's not that you get better results, you get slightly worse results, but you get, it costs you less compute, and that's the important part. That's why it's being done. Because, yeah, I mean, your questions about this everyone has these questions. Now, yeah, at every stage, so at the beginning, it's clear you have an image of a cat. In between, you still have kind of images. And here, with this, we are going to kind of wrap up. We still have a couple of minutes. But these are some example images, visual representations of how some of these kernels look like as you move in the network. And at the beginning, you kind of have these, and these are something that maybe a human would say, well, is there a diagonal line, to the right, to the left? Is there a circle? Some of them are also colored. It's very hard to figure out really what's going on. But this is how some of these, and to be honest now, I don't know which network this is from, because, based on your question, these seem to be pretty large, actually. So clearly this is not AlexNet, I guess. You may want to look at this reference and figure out which network was here, because here it does seem like the input kernels were smaller than the later kernels. Yeah, and so something else than classification. So classification is finding, the sheep, the dogs, and the human. The other is localization. Where are, sheep? Or the other is segmentation, basically identifying the shapes of the different, and then, maybe even identifying one sheep from another, and that would be instance segmentation. Again, CNNs were so successful, and this is before transformers, that people have tried to put different other applications into, so that CNNs can do it. So for example, voice spectrograms, you can have, this is time domain, this is frequency, but you have an image. So now you can use a CNN to, recognize what's there. Yeah, so this is for text classification. So with this, we're just 1 minute late. That's a pretty good thing. Thank you very much. So now it's time for lunch.